Good afternoon, everybody.
Hello there.
It's like in the wrong course here. That doesn't help. Okay, so everybody obviously has a grade, and hopefully you've had a chance to take a look at the key as well and figure out what you did. And if anybody has any questions, you can always email me, and we'll talk about it. So we're going to start on test 3 today. I'm going to specifically be talking about nomenclature. After class, I'm going to send you an email letting you know that the Thursday we come back after spring break, I won't be having an actual Zoom class. Okay, I'll leave you well, actually, we already know what topics we're going to be looking at. So let's take a look at the syllabus. Oh, maybe we don't. No, that's right. Maybe it's in the test 3 folder. I thought I'd done something. Put the days on or something. Here we go. Yeah. All right. Yeah, so you can see the day 1, what we're going to cover today. Day 2, it'll be day 3. So you can watch the day 3 videos, and I'll send an email out about this. That's on that Thursday we come back from spring break. And you'll have plenty of time to get through everything and for the test and whatever. So just that one day. But there will be class on Tuesday. All right. Okay, let's have a look. Test 3 notes, printable. Here we go. No, so starting out, we're looking at carboxylic acids and their derivatives. So I'm going to go ahead and close that up here. All right, let me show you some pictures of what I mean by carboxylic acids and their derivatives. So first of all, this creature here, C double bond O with the OH, we call that a carboxylic acid. Then we've also got something with a C here. That would be some sort of alkyl group. It doesn't have to be just one C, of course, but this would be called an ester. We've got the C double bond O with the Cl. We call that an acid chloride. We've got the C double bond O with the O to a C double bond O, and that's called an acid anhydride. We've got the C double bond O to the N, that's called an amide, and a C triple bond N, and that's called a nitrile. All right, just making sure I've got all of them here. It looks like I do. Okay, so those are all the carboxylic acids and, well, and derivatives. But derivatives are these guys here that I'm going to put sort of in the parenthesis here. So these are derivatives. And by the word derivative, I mean derived from a carboxylic acid. So all of these can be made from carboxylic acids. It's really the bottom line here. Does anybody have any questions so far? Okay. So we have certain names and things that we can talk about as well. We've got, let's start out with naming carboxylic acids. So when you've got a carboxylic acid, what you can see here is that the C double bond O with the OH has to be on the end of the chain. So there's no need to number that as number one. It will always be assumed that it's on the end of the chain. If it's heptanoic acid, it's heptanoic acid because there's 7 carbons in the chain, including the C with the C double bond O. 1, 2, 3, 4, 5, 6, 7. So that would be called heptanoic acid. So you can see the name here, oic acid. So dash oic acid. Any questions? Acid chlorides, because they're made from carboxylic acids, are named after the carboxylic acid from which they're made. The basic reaction here, and we'll talk about this a little bit later, R is going to be anything in general. But we can make acid chlorides in a single step by using the SOCl2 thionyl chloride reagent. And you can see the OH gets turned into a Cl. So this would be called heptanoyl chloride. So it's like it's a YL, the ic acid gets turned into YL chloride. So you can see the pattern there. So the ic acid gets replaced with YL chloride. So it's heptanoyl chloride. You can see the other one here. This is 4-isopropyl 2,3-dimethyl heptanoic acid. So you can see we're just adding on the functional groups as we see them here as well, the substituent groups. Does anybody have any questions? Now the acid anhydrides are also made from acids. Typically they are symmetric. They're made from the same acid. But for simple ones, they can be made in this way by taking the carboxylic acid and dehydrating And you can see that if we take the OH and the H and join that together, that gives us the acid anhydride. So the acid anhydride is named after the acid from which it was made as well. And you can see that this would be simply butanoic anhydride because it's made from butanoic acid. So the acid would be, this is butanoic acid I'm showing you here. So it's a 4-carbon chain. So this would be butanoic anhydride. You don't say dibutanoic anhydride or anything like that because generally they are symmetric. Anything you see on a naming quiz will be symmetric as well. Because it's an anhydride, you know it's got that C double bond O to an O to a C double bond O functional group. So you know that it's 2 acids effectively joined together by the removal of water. Does anybody have any questions about naming acid anhydrides? Okay, so esters are a bit trickier to name. So as you can see, this is going to not be a particularly fun naming quiz, is it? So in an ester, there's two portions, and I've got the schematic over here. So you've got the C double bond O with that part joined to it. That's going to be from the carboxylic acid. And then you've got another part that's from an alcohol. So if we had a carboxylic acid, which I'm just going to put an R in front of, and we react it with an alcohol, and the R primed here is indicating that it's a different R group. Well, well, it could be a different R group from the R that's listed here. It doesn't have to be the same, is what I'm saying. If it was an R, then you'd be saying, well, they're both the same. But if it's R and R primed, well, they're not necessarily the same. Probably different. What we end up with is this, is this product, and you can see that the OH and the H are joined together. That's forming water. But the point here is that if I was to put a square around this, you can see that the square part comes from the carboxylic acid. And if I put a circle around this, the circle part comes from the alcohol. So that's important because now we are going to name the esters, and they're going to be named based on the alcohol and the acid together. And it's the alcohol portion that's always listed first. And then the ic acid turns into O8. So ic acid, let's write this down. So the alcohol, and it's always YL. And then the carboxylic acid, and that's going to be ic acid turning into O8. So this example here, you've got two portions. This part comes from the carboxylic acid with the C double bond O, and then the O joined onto the isopropyl group here is going to be the alcohol portion. So the alcohol that this would have been made from is called isopropyl alcohol. So it's isopropyl. And then you've got the other part, which is the butanoic acid. So that becomes butanoate. So yeah, these are a little bit more complicated to name. Does anybody have any questions so far? So this would be made from propyl alcohol with the O on it, because it's got 3 carbons. N-propyl if you want, or N-propyl alcohol. And then the other portion is 2-chloropropanoic acid. So it'd be N-propyl or propyl 2-chloropropanoate. Does anybody have any questions?
There are 2 words, right?
Yes, that's right. And a space between them, Miriam. Okay, so naming amides. When it's an NH2, it's just named as an amide. Just a straight amide. So this would be 3-bromo-2-nitro pentanamide. 1, 2, 3, 4, 5. That's 5 carbons. when there's groups attached to the N, though, we have to identify which groups are attached to the N. If it's the same group, then it would be capital N, capital N, dimethylbutanamide. Now, on the naming quiz, and we've talked about this before when naming these kinds of compounds, especially anilines, we talked about how I always require that everything be in lowercase. And sometimes people take issue with the N here, say, well, look, that's in uppercase. Well, it isn't. That's actually not an N. It looks like an N, but it really isn't. It's a symbol for nitrogen, which looks suspiciously like a capital N, but really isn't a capital N. It's mind-blowing, isn't it? So that'd be N, N dimethylbutanamide. If they're separate groups, or not the same, then it'd be N-ethyl and methyl propanamide. And we're trying to indicate there that the groups on the N are notified as such, or denoted as such, because they have the big N with the dash in front of them. Does anybody have any questions?
So does this always have to be at the end of the chain?
Yes, it will. Yeah.
Okay.
Well, the end of the chain, the base chain, if you will, that contains a C double bond O.
Okay, so we never have to mention the location. I'm trying to understand.
Well, the location is, if it's off the N, that's denoting the location of those specific groups.
Okay.
So, you can see here that tribromo-2-nitropentanamide, if there was anything on the N, then it would have been like N, say, N-dimethyl would go out in front of this. But this 3-bromo-2-nitropentanamide would be understood to have the nitro group and the bromo group coming off the C double bond O part of the chain.
So which one would, if we had other alkyl group attached to that N with the brom and the nitro, how would we decide what comes first? Alphabetically? No, well, you're saying that N is not a letter, so how would we decide what comes first?
If we had this, it'd be N, N, dimethyl. That would be listed first. And then it would be 3-bromo-2-nitropentanamide. So the portion connected to the N would go first. Mary?
Okay, so it's regardless of if it's alphabetically comes
Yeah,
first.
that's right. That's right. All right, any other questions? The last ones are nitriles, and they're named as O-nitriles. So this would be from heptanoic acid, 1, 2, 3, 4, 5, 6, 7. But the C here that's at the end of the triple bond, we don't see it as a C, but it is a C. So that is included in a chain as well. So that would be heptanoic acid would be the carboxylic acid it comes from. So that gets converted into effectively C triple bond N. And then the other one is benzonitrile, which comes from benzoic acid. So the ic acid becomes, well, the oic acid, I guess, becomes O-nitrile. Okay, any questions? Okay, so let's take a look at the naming quiz here, just so you can get an idea of what you're going to see. I'd recommend doing the naming quiz as soon as you can. I didn't look to see who took the test 2 naming quiz and when they took it. But I know, I suspect a lot of people waited until the night before the test to take it. Well, you know, that's your prerogative, I suppose. Not very wise, but anyways. So you can see that you've got a bunch of questions here. They're all going to be different functional groups. So there's 10 here on the naming quiz. I think you have to get 80% to open the credit quiz. And then let me see, I want to see how many attempts you get on the credit quiz, but I think it's a fair number. You got 10 on the last one, 10 attempts. Yeah, a lot of people don't like this particular naming quiz. All I can tell you, if it makes you feel any better, is that there won't be a naming quiz for test 4. Maybe you can use that to say, oh, okay, well, this is the last one I have to do. The last mountain I have to climb. It's okay. Hang on, I didn't mean to preview it. How many questions are there? There's only 10 questions. That's pretty damn reasonable. I used to have 20 on it or something. Gosh, I must be getting soft in my old age.
I'm feeling pretty silly because I didn't realize there were multiple attempts on the last one. I would have happily taken that last one again.
No. Well, I don't know where it says how many attempts there are when you take it, but I think doesn't it say somewhere when you're taking the quiz?
Yeah, if you click on it before you start quiz, it tells you.
Oh, okay. On the opening page.
Yeah, I was pretty sure it said 1. That's why I.
Oh, okay. Well, it didn't. I mean, it said 10, so maybe you didn't see the 0 next to it, hey?
Possible. I'll go with that.
You don't like zeros, possibly. I don't know. Assessment. That'll tell me how many attempts. 10. There you go, Donna. Do you see that? You get 10 attempts. You get 10 attempts. Yeah, that's good.
Thank you.
All right. Goodie-o. Now, when we talk about the reactivity of carboxylic acid derivatives, you'll remember that the derivatives I listed are derivatives because they can all be made from carboxylic acids. But we can order the reactivity in accordance with the stability of the leaving group. And leaving group is always going to be whatever's attached to the C double bond O, but with a negative charge on it. And you'll see this, even if it's an acidic kind of process, that basically that's what they are. They're the same thing with the negative charge on it. And you can see that Cl negative is pretty stable. And it's like sodium chloride. We know that that chloride is a pretty stable species. Makes up 3% of the ocean, so we know that Cl minus must be pretty stable. The carboxylate, or the C double bond O with the O negative, that one's more stable because the negative charge can resonate between the two oxygens. Then you've got the OR negative for the ester and the NR negative for the amide. And you can see the conditions required for the reaction, how they get more and more brutal as the quality of the leaving group decreases. So the Cl minus needs only room temperature, or the acid chlorides need only room temperature, neutral conditions to react, and then it goes room temperature and acid for the acid anhydrides, reflux, which means heating, acid, that means a acid catalyst, and 1 hour to make an ester. That's what we did with the banana oil. And then with the amide, it is reflux acid 24 hours. So you can see that, you know, we need rougher conditions as the quality of the, or the stability of the leaving group decreases. Does anybody have any questions? Okay. So we're going to start off here with syntheses of carboxylic acids. I'm going to ignore, for now, C, D, E, and F, because those will be incorporated when we look at the reactions of these specific species with water. So you can see all of these result in carboxylic acids from the reaction with H2O. Now I'll get into a pattern here that I'm going to show you. I'm going to put it on the top here and hopefully not forget to not erase it. But there's going to be this situation where you're going to have RC double bond O with a Y, and that Y is going to be indicative of some kind of carboxylic acid derivative. And then when you hit it with XH and H plus, and you'll see this will be a very common pattern, the X will end up replacing the Y, and the H will join the Y. Now this is an acidic pattern or acidic situation. The next one is a neutral situation. And you can see what differentiates a neutral situation from an acidic situation is what's on the arrow, or actually what's not on the arrow. So you can see in a neutral situation, there's no H plus being added as a catalyst. In the basic one, we're using some sort of negative species to react. Same kind of deal. And that'll give the X group replacing the Y, and then Y with the negative charge on it. All right, does anybody have any questions so far? So I will be coming back to that. I'll be coming back to that and leaving it there. Let's get rid of that before it scares people. Okay. First of all, let's start off with the other ways that we can make carboxylic acids. We can make them by oxidation, and specifically oxidation of a primary alcohol. So if you'll remember way back in test 2, we talked about primary alcohols, and if we use a harsh oxidizing agent like CrO3, it'll turn it into a carboxylic acid. If you recall, this is just with the last test, if we use PCC, that gave us an aldehyde. And that's not a carboxylic acid. So we have to use something harsh. CrO3 is the reagent of choice. No mechanism there that I want to share with you. It's really too complicated, but if you just know that we can get carboxylic acids from primary alcohols, then you know that's good. Does anybody have any questions? Okay. Another way that we can make carboxylic acids is by taking a Grignard reagent and adding carbon dioxide to it and then protonating it. Now, I'll make a comment here. I noticed that on the last test, sometimes, well, in the synthesis problem, I think it was, well, it was the first problem 5. I know there were 2 problem 5s, I understand that. But the first problem 5 was a synthesis problem, and a lot of people didn't include the 1 and the 2 out in front. And that's important because the 1 tells you need to put something in first, and then the second one tells you have to put something in later. The reason that's important is because if you don't have the 1 and the 2 here, you're saying that everything's going in together at the same time. And when you don't want to do that, because oftentimes it's because these 2 things will react with each other, or the H plus would certainly react with the Grignard reagent, then you don't want that to happen. So you need to do 1 and then 2. So the mechanism for that one, the CO2, by the way, is like dry ice. You've all seen dry ice before. So just plonk. That didn't work out so well on the arrow. Let's try that again. Now, one thing you'll notice here, the difference between the first method of making a carboxylic acid and the second method is that the second method actually adds a carbon to the chain of what we're starting with. So this has 4 carbons, and the end product here still has 4 carbons when we use the harsh oxidizing agent. When we're using the CO2, we're starting off with 3. We're starting off with 3 carbons. And we're finishing with 4 carbons. See, the extra C comes from the CO2 itself. So when we're talking about synthetic processes, whether we're adding an extra C or not adding an extra C might have an impact on how we might make a carboxylic acid. Does anybody have any questions? So as I said, these other ones, C, D, E, and F, we will talk about as we go through reactions of these with water, which we haven't done yet. But still, it's good to be aware that, well, if we take the acid chloride hydrolysis, for example, I'm not going to do all of these, I'm just going to do one of them just to show you something. So I had this pattern over here. So I'm splitting the water into HOH. You'll see why in a second. You can see that it would match the neutral one here because there's no H plus and it's not negative. So it's going with the neutral one. And you can see the pattern here is that the OH, which is going to be like the X, and the Cl, which is like the Y, and you can see here the X replaces the Y, and then the Y group would be HCl, so that'd be HY. All right, does anybody have any questions? You'll see this a lot, so that's just my first.
I have a question.
Yeah.
So I see that there is a proton absent in, I'm sorry, the reaction that you're just covering under acidic and neutral. But
right.
The final product is the same?
Yes.
What would be the...
Because the H plus is a catalyst. It's there in the beginning, it's there at the end. It's only the XH that's actually doing any reacting.
So it's not really doing anything to the reaction?
Well, it's speeding it up, but it's not really changing anything with regard to the products, Miriam. You'll see that when we actually go through these specific mechanisms, okay? So here we've got the synthesis of acid chlorides. I think I'm just going to check on the, just want to check on the syllabus here. See exactly how far I want to get today. I don't want to check on the syllabus, do I? No, I don't want to do that. I want to check on the videos. That'll give me a better indication how much we have to, what we have to get to. Looks like synthesis of esters, reaction of acid chlorides and alcohols. Okay. All right, so that's as far as we're going to go today. But we're looking here at synthesis of acid chlorides. I touched on this earlier, and I said that thionyl chloride, SOCl2, can be used to convert an acid into an acid chloride. This is the mechanism for it. I don't really want to go through the mechanism. If it appears on a test, you could get a bonus point for it, but I'm not going to ever put this mechanism in as an actual mechanism that you have to do for credit. So I'd call this optional or oddball. Yeah, I'm going to go through all these reactions later and just tell you exactly which ones are possible for, or what they're called, you know, whether they're acidic, basic, neutral, and we've already been through that. And then there's another one I'm going to say O for other, or oddball, or optional. We'll just say other or oddball. I don't want to say optional because then people think they don't have to do and you have anything to do with it at all. But no, we'll just say O for other or oddball. This is an oddball. Does anybody have any questions about the mechanism itself? So like it was with test 2, the products I'm expecting you to show are anything with carbons in it. In this instance, SO2 and HCl don't have carbons, so you really don't have to show them as products. You can, but you don't have to. You'd certainly show them if you're doing the mechanism, but not if you were just writing out the product. So it's not a difficult pattern. You can see the OH gets turned into Cl. Not very much change there happening at all, really. Okay, does anybody have any questions? Okay. Acid anhydrides. I'm actually going to show you, well, I'm going to show you a second one here as well. But there's another way that we can create anhydrides. And this only works if it's very simple though, is if we take a simple carboxylic acid and we heat it, we can dehydrate it and turn it into an anhydride. That's not a reaction you have to be particularly concerned about, but I'm mentioning it there because it is a possibility. And what it requires though is 2 moles of the same acid. And you can see that we lose an H, we lose an OH, that forms water. And then the O joins onto the C double bond though. Does anybody have any questions about that? Okay. So I just mentioned that as another possible way of doing it. The other method allows us to make, well, what I'm essentially calling asymmetric acid anhydrides, which means the different R group on each side. And we can do that by, first of all, making a carboxylate ion, which means we take a carboxylic acid and we add add a base to it, sodium hydroxide or sodium bicarbonate will do a trick. And what that will do is take the H off the carboxylic acid. You see, the thing about carboxylic acids is that they are, by their very nature, acidic. What does that mean? It means that in solution, they break up at least minimally into a negative and an H plus. So O negative and H plus. We can force that issue by adding a base like OH minus in order to make that happen. And then that negative O can react with an acid chloride to create an anhydride, an asymmetric anhydride to be more exact. The mechanism it's following is based on the basic mechanism over here, and I'm going to show you all three mechanisms here that I'm calling acidic, basic, and neutral. These are just the reactions, but I'm going to show you the actual mechanisms for them, because that's kind of going to be important for us down the track. So I'll create another, let's see, have I got another window open? Maybe this one. Yeah. I'm going to save this file as well because I'm going to be using it a lot in the future. Now with the H plus here, so Miriam, you were asking about what the H plus does. So it's going, you'll see what happens and why it's catalytic in a second. So what's going to happen here is something that was a little bit different to what happened when we dealt with the aldehydes and ketones in the last test. What I'm showing you here is pretty much the same. But what's different here is that Y is a leaving group. So the proton gets transferred to the Y group, which is always whatever was originally attached to C double bond O, so that's never a big mystery there. And whenever I'm talking about acidic mechanisms, this is what I'm talking about. In the last step, the double bond O reforms and we end up losing the leaving group. But what I want you to see here is at the end, we have an H plus formed, plus we have YH. So the H plus is there at the beginning and there at the end. That's what makes it catalytic. In the case of neutral, that's when we don't have an H plus on the arrow. So what makes this one a little bit less favorable is the fact that you're forming this thing that's got a positive and negative charge in it. And those tend to be very unstable species. All right, let's see. And this is basic. It's the last one. And then the X minus attacks, and then the negative charge comes down and kicks out the Y. And we get the C double bond O reformed along with the Y minus. All right, does anybody have any questions?
Yeah, I do.
Okay. So the mechanism that we're looking at here for this one would be the basic one, because the O negative is what's going to be attacking the C double bond O. And by the O negative, I'm talking about this one here, this X negative, that's the X group there. And what's being taken out is the chlorine, which is the Y group. And that leads to the carboxylic acid, sorry, the acid anhydride as a product. Does anybody have any questions about this reaction?
Dr. Musgrave,
Yeah.
for the neutral, why can't O negative get protonated by that hydrogen and leave?
Which hydrogen are we talking about?
In the neutral, where we have the
Oh, I see. Okay, hang on. All right, let me see. Let me see acid. Let me save that. All right. So the neutral here. What are you concerned about here, Mariam?
yeah, so I'm saying, why can't the O negative be protonated by that hydrogen and then leave, rather than reforming that double bond?
Because the leaving group leaves faster than that can happen, because the leaving group is more stable in that situation.
Okay, so you're saying Y is a better leaving group than OH would be?
Yes, that would be true. Yes.
Okay.
But you can take it to the bank that what's going to happen is whatever XH is going to replace the Y, and the H that was on the X goes with the Y. It's a fairly simple pattern. It's almost like a substitution of sorts, but it's not a direct substitution or a one-step substitution. It happens in a couple of steps.
Okay, thank you.
Okay. So I would call that a basic mechanism, by the way, for that one. Now the next one, synthesis of esters. There's there's a few we're going to be dealing with. We've got methyl esters, and this is from diazomethane. This is an oddball reaction because, again, it doesn't fall into any of these three categories that I have here. And diazomethane it's a yellow gas. It's very explosive, very toxic as well. And what you do is you sort of add it. It's usually in a solution of diethyl ether. It's a gas, but it's in a solution of diethyl ether, yellow liquid. And you add it to a carboxylic acid, and you'll see nitrogen gas bubble off. That's the N2. And then it's usually a colorless solution initially, and then once it becomes yellow, you know you've added enough diazomethane to it. And it's a very efficient way to create methyl esters specifically. That is OCH3. So the CH3 group, remember, is a methyl group. And again, that's an oddball or other type reaction, if you remember, because it's not falling into any of these three categories here. Does anybody have any questions about the diazomethane reaction? Again, if you want to learn the mechanism, you can. It would be useful if this turned up as part of question 1. Okay. Acid chloride and alcohol. So take a look at this one. I'm going to do a quick poll here.
And we still see your screen, just FYI.
That's okay. It doesn't give you the answer.
I figured, what if you're going to pick one and then we'll see it and then you'll have to redo it all over? Since
I don't have to pick. It's a poll, so I don't have to pick. You'll see in a second. See, I just saved that as a poll, and you guys are the ones that actually do it. You'll see in a second. So polling, I pick this one, and then I launch the poll. See, there's no answer. You guys have to pick.
Okay.
All right, let me go back to the actual question here. Oops, there we go. So we're talking about the acid chloride and alcohol. What you think? Sorry, I'm covering up something that I shouldn't be covering up. Sorry, hang on. There we go. Okay, all right. So let's see, 6 of 21 have answered. I'll give you 10 more seconds. 10 more seconds to make a decision. 5, 4, 3, 2, 1. Ending the poll. Show results. So most of you, well, at least 42% of you said it was neutral. Neutral is correct. So what defines it as being neutral here? Well, look at the actual reaction itself. Do you see how it's just got nothing charged on the arrow? That makes it neutral. In order for it to be acidic, it'd have to have H plus on the arrow. For it to be basic, it has to have something negative on the arrow. Anybody got any questions? So you can see that it's going to be based on this neutral mechanism. So I'll let me pull up another window here. and I'll do an example. So look at the pattern here that I was talking about earlier. Notice how I can always get the product just by applying that same pattern. That this is the, let's see if I've got the thing here. That, you know, generally what we can talk about is the X group, which is attached to the H. So that's the chain with the O, replacing the Cl, and then the H from that chain joining onto the Cl. Does anybody have any questions just about the pattern? Now, as far as the mechanism goes, I'll show you. We're just applying that second mechanism there, the neutral one. There is no H plus in the solution, so I can't use that. So Miriam, you were asking earlier about why the H plus didn't go up and protonate the OA, the O here as a negative. What happens is that this Cl leaves because it's a very good leaving group. A better leaving group than the OH would be, definitely. So that forms Cl negative, and this is still joined to the H plus. And then we can lose the H plus, and that forms the product. Which is going to be that, which is H plus and Cl minus, which would be HCl if they join together. All right, does anybody have any questions? All right, let me see how far we're supposed to get today. Again. Yeah, that's as far as I want to get. All right, so on Tuesday, there will be a class on Tuesday. We'll start on the day 2, whatever's going on day 2, we'll get through that. And then day 3, you should watch those videos yourselves. And then, you know, we'll probably go over them again before the test, but you know, I want you to watch those videos. I want you to watch that instead of attending the lecture on next Thursday. All right, does anybody have any questions?
Yes, I just want to confirm that test 3 is going to be on April 1st.
All right, let's take a look at the syllabus and we'll make that determination. Yeah, so it looks like test 3 is on Thursday. Yeah, the Thursday of that week, March 29th, Monday, March 30th will be Tuesday, 31st will be Wednesday, so April 1st will be test 3, yeah. It's not April, not some sort of April Fool's joke. Okay, any questions?
You said next Thursday, don't come to class, just watch day 3 videos?
That's right. Well, Thursday after spring break, Deanna.
Okay.
Yeah. Okay, any other questions? All right. Well, we'll leave it there for today then, and I will catch up with you all after spring break. Have a good spring break.
Thank you, you too.
No, thanks.
Thank you, Dr. Musgrave.
All right, bye.
Bye.
Dr.
Dr. Musgrave,
Yeah, Courtney.
would you say this test is similar to like test 2 in a way? Like
It
you
is
said
similar, but more involved because there's definitely more reactions.
Okay.
In this case, it's like 45 reactions for this test.
Oh,
But-
okay. Yeah.
But a lot of them, or 90% of them at least, follow one of these 3 patterns:
Okay.
acidic, neutral, or basic mechanisms.
So knowing those 3 will
Yeah.
basically.
It will help you immensely. Yeah.
Okay. For getting ahead, since we don't have class for a week, would you say to like just watch the mini lectures and try
Absolutely.
to get?
Yeah, that would be a fantastic idea. Yeah.
Okay. Perfect. Thank you. Have a
No
good
worries.
week.
Thank you. Bye-bye.
Bye.
Dr. Musgrave?
Yes.
It's Donna.
Yes,
I don't know.
Donna.
I can't, you're still sharing.
I'm still sharing. Okay.
I was hoping, yeah. Can you take a gander at that last question, part C of number 5
Yeah, I
on
think
the
it's just
test 2?
I think it's just you and me on the call here, so
I think
we
you could
have
stop recording.
in fact, I will do that. That's a great idea. Why
Thank
don't I
you.
do that? Thank you. That saves me a lot of trouble. I don't want to have to go back and
Yeah.
stop
Edit.
recording later. I just got to. So where is it? End.